really what we're trying to do here is bring blue hydrogen, the levelized cost of blue hydrogen down, and bring that carbon abatement up. And the way that we see that should be done is pre-combustion carbon capture. So we'll go through that and how that's done a little bit later. And some other advanced sort of methods to try and bring that cost of the plant down and the hydrogen yield up. So I think the really important thing about this, I apologise that you have to look at this slide probably 5 times in the hydrogen conference, and thankfully there's no pink ones and white ones and gold ones in here as well. But the really important thing is the phase of it, right? So this is grey hydrogen. We're using methane, SMRs, ATRs, but we can basically already do blue hydrogen. We've got the technology, we've got the reformers using natural gas, and we then just need to capture that carbon, which is something that we're doing today at scale. So we have those technologies, and the technology gap and that technology readiness level is much improved versus those more advanced methods that my colleagues have been talking about. And I think that graph that was shown earlier was really powerful, because what it shows is we need to get on with blue right now. We need to get it started at scale, and then we need to add as much green as possible as that scales up. So there's going to be room for both of those, really. So a little bit of background on wood and its SMR technology. As we heard a little bit earlier, we've built an awful lot of these plants over the years. So it started in the 1960s. There's a lot of 70s and 80s vintage plants still around. They're still reliable, they're still going, they're still relied upon. A lot in refineries and other such industries, rather than the sort of gigawatt scale plants that we're seeing being developed now. So we've supplied over 220 of our terrace wall reformer furnaces, which is really the core of these reformer technologies, and built over 120 of those plants over the years. So an awful lot of development over the years, but there's still more to go, and there's a couple of these technologies that we're trying to push in now that really just raise the bar again, especially when we're talking about decarbonising. So as you may know, there are 3 well-proven and really good technologies really for producing hydrogen, and you can bolt blue onto any of these really. So the autothermal reforming, so this has traditionally been for really big reforms, big hydrogen production, syngas production. It does require catalyst, it does require an air separation unit, but there's a really good installed base for that. Partial oxidation, you'll have seen as well. There's no catalyst involved with that, so that's a positive. But it does require that air separation plant. So again, it's quite resource intensive from that perspective, and CapEx intensive. And then we've got a pretty well proven steam methane reformer technology. Again, it requires the catalyst, but doesn't require the air separation unit. So in a nutshell, those are kind of the comparisons. Obviously, there's lots of PFDs behind that, process flows, which I'm not going to bore you with today. But those are the 3 that you'll be familiar with, and we'll compare those in a minute. So just rolling back to what steam methane reforming looks like in a grey sense. So we've got three modules to this, if you like. So there's pre-treatment, so where you might remove some of the sulphur, we've got some compression going on, some preheating, adding the steam in as well. We've got the core of it, which is this reforming part where we've got a terrace wall, if it's a wood one. There's some heat exchange going on, and then we go into a shift reaction where we produce more of that hydrogen. and then we start separating that. So any of the non-hydrogen, other off gases, that gets routed back into the furnace, and you burn that off, and then you're left with your hydrogen. So how do we convert that to be something that we can call blue, and to a really great extent is blue? So the integration that we've done here is between the shift reaction and that separation. So we install this pre-combustion carbon capture, and this is really important. So you can do pre-combustion or you can do post-combustion. And pre-combustion means that we've got something that is high pressure and it is lower temperature, and it's got relatively few of those impurities in it that cause a lot of problems for carbon capture. So from that perspective, it reduces the capital cost of that carbon capture, which is really important, because I guess in our minds we think carbon capture is just a column, it's just an amine column, you just plug that in like a hydrotreater. It's just a tiny thing on the end. It's not. These columns are huge and massive plants. So the more we can do to reduce that side of it, the better. And I suppose the other thing that isn't perhaps mentioned on here is that we've also altered that process so that we're decarbonising that fuel that goes back into that steam reform. So you put all that together, and we can get to that 95% decarbonisation, which is a really good target for this. There's two technologies that we launched to compete with those other processors this year. So the blue SMR, which we've just basically seen, and this blue SMR Plus concept. And really the difference here is we're adding in a heat exchanger with catalyst in it that means that we have to produce less steam from this process, and we're able to produce more hydrogen from it. And when we're looking at levelized cost of hydrogen, which is what we're really all bothered about here, what's the minimum cost we can make that kilo of hydrogen for? That's obviously what we're aiming for. We don't want to make steam, we want to make more hydrogen. So that's what that gas heated reformer does. So what is it? It's basically a vertical tubular reactor that's then filled with a nickel-based catalyst, and then that's effectively acting as a heat exchanger as well. So it's really high temperature from the outlet of the reformer, and then contacting that heat effectively with the feed. So then it's converting more, it's able to generate less steam in the rundown, and produce more hydrogen for the volume of the plant. So let's talk about scale a minute, because SMRs, I think, traditionally have been looked at in a refining or smaller scale context. But really, the things that we've been talking about today have been sort of gigawatt stuff scale, which is a different thing. And they're used in, so mining, we've got a picture of mining there, we've got home heating, so national scale usage, and that's the sort of targets we're looking at. So I think it's more important to look at this sort of gigawatt scale. So this 300,000 normal meter cube per hour, that's kind of that gigawatt, 1 gigawatt scale. And I think what's really exciting now is that the potential purchaser of one of these, or the operator of one of these, they can choose from a variety of technologies here. So if we look at the IEEE Ghg Benchmark, which is on the left there, that tells us what the world authorities are telling us what the carbon dioxide emissions should be, what the capex should be. And you can see that all of these advanced options that we've got here are actually doing better in most cases, perhaps apart from the ATR in terms of the decarbonisation. So you can see here there's a really wide range of cost. They all do pretty well at decarbonising, but in terms of cost, it's quite a big range. So The standard ATR is, I mean, we're talking about a couple of 100 million here in terms of that standard ATR versus those wood and blue SMR pluses. And what we've also done, just to level the playing field a little bit, is we've applied that gas-heated reformer technology into that ATR technology, just to make sure that we take advantage of that in there as well. So there's definitely better and worse technologies here if we're looking at reducing levelized cost of hydrogen to its absolute minimum. And just digging into that a little bit more, this graph, which unfortunately you can't really see the axes very well, this is just levelized cost of hydrogen moving through the same cases as before. So finishing with those SMRs and running from the POX units and the ATRs. I think one of the important things to see here is the power consumption that goes into the air separation units for two of those technologies is quite significant, and also the capex associated with that air separation is also very significant. So if you build all of that in, it actually starts to create quite a difference between those technologies. So in summary, we've presented what our solution to this blue hydrogen demand is. We've also had a look at some of those other technologies which are also absolutely valid in getting to that final decarbonisation endpoint. There's a couple of technologies that we've released this year. Absolutely happy to share those with you. But I think the key thing is that we need something that's proven today. Right? If we're going to start building at scale blue hydrogen capacity, we need something that we can rely on today. Otherwise, we might as well wait for green, if I'm honest. And SMR does deliver that effectively, as do some of the others. So that there are those technologies, we have that ability, so we can start this today. Thank you.